Hello and welcome to video 1 of 2 on Chapter 13. Now, Chapter 13 introduces us to the concept of magnetic induction. And the idea is that you can use either a magnetic field that varies in time, an area that varies in time, or a combination of the two to induce a current in something that is not directly attached to a power source. So, before we get to that, what I'd like to initially talk about is one of the necessary concepts that we need to discuss in order to talk about induction, and that's magnetic flux. Now, we briefly talked about this last chapter. However, the idea of flux is not a new one to us. If you remember, we talked about the electric field, we talked about electric flux, and then we made the jump from electric flux to Gauss's law when you consider, the motion of an electric field through a closed surface. So that said, magnetic flux is defined in a similar manner as electric flux is. We're going to use capital Phi sub m, and really all it is the integral of b dot n hat ds. Now, this is not a closed surface that we're integrating over. This is an open surface. Remember, closed surfaces for magnetic fields generally give us a net flux of 0 whenever we consider them, because the flux in and the flux out is the same in magnitude, just opposite in direction. So here, if you consider sort of a surface sitting out in space, and maybe this is the direction right here of out from the surface. This would be the normal, right there. So here's our surface S, and maybe here's some magnetic field that's entering the surface and then passing its way through like that to exit. So here's B. Then really all we're looking at is the amount of magnetic field times the surface, or really it's just the amount of magnetic field that makes its way directly through. Because remember, the dot product here is ensuring that we get the part that goes in and out and not that rides within the surface itself. So, if you look at the units here, we know the MKS units for a magnetic field, or the Tesla. Surface is meters squared. And this set of units actually is called the Weber, abbreviated WB. Okay, so just a quick example. Here, what is the magnetic flux through a 1 square meter metal grate that sits level on the ground? There's a magnetic field which has a strength of 0.6 Gauss and enters the Earth's surface with an angle of 20 degrees with respect to the surface. So what we have here, I guess it's poorly written, but we have our metal plate like this, which I'll sort of draw on edge a little bit like that. So this would be level to the ground right here. And then we have the Earth's magnetic field that comes in like this, making an angle of 20 degrees with respect to the surface right here. Now, what's meant by that is that if you were to draw the surface normal, it would actually be out in this direction like this. Like that. So there's your normal. This is the magnetic field B right here, and this would be the angle 20 degrees. So what we're given here is that our surface here is 1 square meter. Our magnetic field B is 0.6 Gauss. Now, if you remember correctly, there are 10 to the 4th Gauss in 1 Tesla. So this would be the same thing as 0.6 times 10 to the minus 4th Tesla, which puts us in MKS units. Our angle here is 20 degrees, and really that's what we have. So what we want to do is define the flux. So our flux here in integral form is b dot n hat ds. So you're integrating over the area that the magnetic field is passing through. Now, here our magnetic field is constant. And if you look here, the dot product between b and n hat is going to end up being a constant number, but it's going to be negative because b passes into in the direction of out is in the opposite direction. But it's going to be constant. So really what you're doing is you're integrating over the surface, and here the surface, we know what that is. That's 1 square meter, which means that this is the same as just b dot what I'll call s vector, or the magnitude of b, the magnitude of the surface vector, cosine at the angle in between. And if you were to extend this through, you would have an angle that would be greater, than 90 degrees, would give you a negative sign. But we're going to work with that angle and note the fact that if you use the big angle or if you use the small angle, you get the same number. You just get a different sign. So there's a minus sign in front. So this is minus 0.6 times 10 to the minus fourth Tesla times 1 square meter times cosine of 20 degrees. So let's see here. Grab my calculator. It is 0.6 times 10 to the minus fourth times 1 times cosine of 20 minus 5.64 about times 10 to the minus fifth Webers. Now, so that said, what I'd like to do now is to consider a specific case. I want you to imagine a setup like this. We have two circuits that are side by side. You have one that's open that has a battery. You've got a resistor here. And then you have one that has no visible power source. It's just a closed loop that has a resistor attached to it. Now, Faraday, who was a physicist back in the day, discovered that were you to close this circuit, what you would discover if you measured the current inside this circuit was that the act of closing this created a momentary current that flowed in here. Now, we know from our discussion last chapter that when you close this, what that does is to enable current to flow. And we know because of the Biot-Savart law that that current is going to produce a magnetic field. Now, here, the conventional direction of current flow is this way around the circuit like that. If you were to take and put your thumb in the direction of I and wrap your fingers around the wire, what you'll discover is that in this circuit over here, you would have magnetic field that goes through the area of it like this. And if they're directly side by side, it would be going straight up through, like that, as a consequence of the current flow. Now, it's a few observations that were made when this particular experiment was carried out. The first thing is this. When the circuit was closed, you had momentary current flow. Now, once the current in what I'll call circuit A became constant, because it builds from 0 to its, Ohm's law current. The current in what I'll call circuit B vanished. The third thing they noticed was that if you were to open the circuit and cause the current to stop flowing, you would have, again, a momentary current flow. In B, once it was turned off. Now, there's another observation that we're going to talk about here in a moment. But what I'd like to point out here is that when the current here is flowing through at a constant rate, the magnetic field that circuit B is experiencing is constant. But when you take and you turn the switch on or you turn the switch off, what happens is the current builds either from 0 to whatever its maximum is going to be, or it dies from its maximum to 0. So what that does on the right hand side is to cause a current that changes over time. Okay? So if you think of the current that was produced in circuit B as due to voltage, just like the current in circuit A is due to, or instead we'll call it EMF, then this changing magnetic field somehow induced an EMF that could drive the current. Okay? Now that's the basis behind what we call Faraday's law. Now I'd like to also point out that you can get the same result here if you were to close the current or close the switch here and just let current flow through here at a constant rate, and then take the circuit and change its area over time. When you change the circuit's area over time, what you'll discover is that you get a constant current flow. So it's a combination of the magnetic field and the area that the magnetic field's passing through. In other words, it depends upon the magnetic flux. So Faraday's law says the following. The induced EMF is equal to minus the change in the magnetic flux through our closed loop circuit over time. This is Faraday's law. Now, this is for a single loop circuit. We know that you can have multiple loops, like for example in the case of the solenoid. So a more general form of this would just put an N out in front, because it turns out that that's exactly the relationship. And you still have your changing magnetic flux over time. Now Faraday's law, it turns out, is the basis behind generators. And we'll be talking about that in the second video. That said, what I'd like to do is to work with this a little bit. Specifically, let's take a look at this problem right here. In this problem, we have a 10 by 10 centimeter closed loop. It has a 15 ohm resistor in it. And what we're going to do is we're going to create a magnetic field that starts off at 0 and builds to about half a Gauss in a hundredth of a second. Now we're going to have the direction of the magnetic field pass straight through the area of the loop, so that the angle between the surface normal of the area and the magnetic field is 0. That's just to simplify things. What I want to know is what the EMF is going to be created. I also want to know what the current is, and also its direction. And when we talk about direction, I'm also going to talk about another law called Faraday's, no, not Faraday's law, but called Lenz's law, that helps us figure out direction of current flow when you have induction like this occur. So what I'm going to do here to sort of draw our circuit is kind of draw it on edge like this. We'll do it like this. So C2. Actually, the easy way to do it would just be this way. Just like that. Then so here's our circuit. What I'm going to do is to carve a little bit of this out and put my resistor there. So here's my resistor. It's 15 ohms. If you think of this, like I said, sort of sitting sort of at an angle on edge, this will say is the direction of our surface normal right here. Our magnetic field initially is 0, and it's going to build to a maximum magnetic field, which we're going to let lie again in the same direction as this. And if I were to just draw a simple coordinate system, which I'll go ahead and do, just so it's a little more clear. We'll call this Z, this Y, and this X. What I'm going to have is I have my magnetic field build to about half a Gauss along the Z-hat direction. So as it builds, the direction of the change of the magnetic field is going to be this way as well. And it's the change in the magnetic field's direction that's going to help us determine the direction of the current flow, which we'll be talking about here in a moment. Now, we also have the dimensions of our circuit. It's 10 centimeters by 10 centimeters. So this right here, this is 10 centimeters. Just like this right here is 10 centimeters. I'm going to call this L. So what we're given here is an initial magnetic field of 0, a final magnetic field of 0.5 Gauss in the Z-hat direction. Our circuit is a square. It's L by L. Each side is 10 centimeters or 0.1 meters. We also have a resistor. It's 15 ohms. Now, we also know how long it's going to take for this thing to build to half a Gauss. That is 0.01 seconds. And what we're trying to find are two things. We want to find the EMF, and we want to find the current, including its direction. Now, so that said, let me scroll this down just a touch. Let's write down Faraday's law. Faraday's law says the induced EMF looks like minus N times how the change in magnetic flux occurs over time, how it looks over time. Now, here N is equal to 1 because we only have one loop, which means that this would be the same thing as d magnetic flux over time. Now, what's the magnetic flux? It's the integral of B dot N hat ds. Okay? So, if you think about what's changing in this integral, it's not the area. The area is L by L. So that doesn't change. The magnetic field does change over time. But the integral right here is not over time, it's over area. So we can pull this magnetic field out because the flux itself over area only depends upon B. Okay? So you could think of this in many ways as just being the change in the magnetic flux over time, like this. So that would be your final flux minus your initial flux divided by the change in time. Now, what's your initial flux? Well, that's going to be B dot or B naught dot S. S is L by L, but B naught is 0. What's your final flux? That's going to be your final magnetic field dotted with the surface. Well, your final magnetic field is going to be pointing in the same direction, which means that dot product is 1, which means that this is just B times L squared. Why L squared? Well, the area of our loop is L by L. It's a square. So the magnitude of the EMF, and the minus sign here is in part due to it's there to allow us to do differential equations and some complicated math with it, but it's also there as a reminder to telling us don't forget about the direction of I, which we're going to get to here in a moment. So the magnitude of my EMF, is just going to be the flux divided by the change in time, or B L squared over delta T. Half a Gauss is 0.5 times 10 to the minus 4th Tesla. L is 0.1 meters. We have to square that. And then we're dividing it by 0.01 seconds. So what's my EMF? .5 times 10 to the minus 4th times 0.1 squared divided by 0.01. Or 5 times 10 to the minus 5th volts. So what's the current? Well, let's just get the magnitude first because that's super easy to do. We know V is equal to I times R through Ohm's law. I is just going to be V over R, or in this case E over R, which would be 5 times 10 to the minus 5th volts divided by 15 ohms. So if you take that, you divide it by 15, you get 3.33 times 10 to the minus 6 amps. So we have our EMF. I don't know why I chose that. I want this. We have our EMF. We have our current. Now let's talk about direction. So the rule that tells us about what the direction of the current flow is going to be is called Lenz's law. And Lenz's law is actually pretty easy to get. You remember earlier how I said it's this direction of the change in magnetic field that's going to tell us about the direction of current flow? Well, here's the deal. Okay, so I want you to imagine this problem and think about the two possible directions that you have for current flow and the magnetic field that they're going to create. So one potential direction would be that your current flow is going to flow around this way. So it's going to flow around, counterclockwise like that. So what if that was the case? So initially your current is 0. As it builds, your current starts to flow this way. And what happens is if you were to put your thumb in the direction of the current flow and then loop your fingers around, what you would discover is the act of the current flowing, it it's starting to flow, is going to create a magnetic field or a change in magnetic field that's going to go like that. Okay, so it starts from zero. As it builds, you have current flowing counterclockwise. Your right-hand rule says that it goes up through the circuit in the same direction as the magnetic field that's creating the current. So what happens is this: is you have a feedback loop. So the current starts flowing. Delta B is doing its thing here, but then you have this extra delta B that's a consequence of the induced current. And what that does is to add to this, which in turn adds to the current, which in turn adds to this, which in turn adds to the current, which in turn adds to this, which in turn adds to the current. And what you have is your current build exponentially to infinity. And that violates conservation of energy, because that energy that's required to move that electrical charge around the circuit has got to come from somewhere. So it builds without bounds. On the other hand, what if the direction of your current flow is this way? What if this was the direction of I? Well, here, if you put your thumb in the direction of I and you loop your fingers around, what you get is an induced current that creates a little bit of magnetic field that goes like this. And what that does is to oppose this. It takes away from it. So as a consequence, it doesn't violate conservation of energy. So the answer to our question here, what direction does the induced current flow, is going to be that it flows clockwise around the circuit like this. That's the only possible direction that it could flow and not violate conservation of energy. And that's basically what Lenz's law says. Lenz's law says that the direction of the induced current is such that the magnetic field that it creates opposes the changing flux that's creating it. Okay? So the whole purpose is to conserve energy, and that's what Lenz's law is sort of a reminder there for. It's what the minus sign you could think of here as being a reminder is for. It says, hey, when you choose the direction of I, make sure you do it so that you don't violate conservation of energy. So let's take a look at this problem. Here, what we have is a constant magnetic field that cuts across the area of a circuit. Now, the circuit itself is defined by a resistor, which is, of course, attached to wires here. But these are incredibly long wires like that. And I have a metal slide here that is free to slide back and forth. So what I'm going to do is to start this slide off with an initial velocity of about 25 centimeters per second. And what I'd like to do is to take a look and see what the current looks like, running through the circuit. I'd also like to know how the dissipation of energy by the resistor here affects the motion of this, because the resistor itself is going to dissipate energy because it converts electrical energy into heat, and that energy has to come from somewhere. Now, unlike the previous example here, where we had a changing magnetic field with a constant area, here we have a constant magnetic field with a changing area. As this thing slides to the right, what it does is to make the circuit grow in area. And as this magnetic field penetrates the additional area, what it does is to create a changing flux over time. So what we've been given here is a resistance of about half of an ohm. We have an initial velocity of 0.25 meters per second. The length of our circuit this way is 10 centimeters, or 0.10 meters. And our little slide here, which you could think of as sort of a, like a little flat sliver of metal that slides frictionlessly across this. It has a mass of about 30 grams, or 0.03 kilograms. And finally, our magnetic field here, which is constant, is 0.25 Tesla. So let me define a coordinate system here just to make our lives easy, so we have something that we can kind of talk about this with respect to. So what I'm going to do is to call this right here the x-axis. Whoops. Probably should have chosen a line to do that. So this right here is going to be the x-axis right here. And, you know, if needed, we'll call this the y-axis right there. So as drawn, the magnetic field is coming out towards us. This is B right here. And so it would be straight up the z-axis if you wanted to think of it like that. Now, so so let's take a look at Faraday's law. We have our EMF, which is minus the change in magnetic flux over time. And our magnetic flux, let's not forget, from a differential standpoint, is going to be B dot n hat ds for our area. Now what I'm going to do is to plug this into this, noting the fact that B itself doesn't change with respect to time, it's constant. The direction of out for our surface, which would be straight down the z-axis in the same direction as the magnetic field, that doesn't change, and in fact the dot product between these two is just going to be 1. But what does change is the area. The length here doesn't, but as this thing grows, the width is definitely changing. So, d magnetic flux here really is just equal to the magnitude of B times ds. And if I plug that into this over here, I have B times ds dt. So S, remember, is our area, our surface. And ds itself is going to have a length L, and it's the width that's changing, and that's in the x direction, so that's dx. Okay? So here, if you look, our EMF is equal to minus B times L times dx dt. And dx dt, we know what that is from University of Physics 1. That's B times L times V, our velocity. Okay? So as this thing changes, or as this thing slides to the right, and the velocity decreases because the power in its motion is, or the energy in its motion is being dissipated by the resistor, then what's going to happen is as it slows down, the EMF is also going to decrease as well. So how do we relate the two? Well, remember, power is the change in something's energy, which I'm going to use E for energy here. I know we've sort of reserved it for the electric field, but just to remind you, it's the change in energy over time, so it's E dt. And here, the energy that's going to be changing due to this resistor consuming energy from the motion is going to be the kinetic energy. And it's going to be a negative change because it's going to be slowing down. So I'm going to call that dk dt. All right. Now, we also know the relationship between voltage, resistance, and current with respect to power. We know power you can write as I times V, or I squared times R, or V squared over R. So what I want to do is to use this particular form here. Excuse me. For power, that's going to be, instead of V, it's EMF squared over R, which when you square this, that's just going to be B times L times V over R, and this is squared right here. Now, so that said, dk is the change in our kinetic energy, and like I said, it's going to be negative, so we're putting a minus sign there to remind us that this right here is taking energy away from this. Now, kinetic energy, if you remember, looks like 1/2 mv squared for things that slide. Now here the mass of this object isn't changing. The only thing that's changing is the velocity. So when I take the differential of that, what happens is we're really taking the differential of v right here. The 2 comes down and gets rid of the half, and we're left with an mv times dv. So that would be the differential, which means that when I relate this to this, it's the same thing as m times v dv dt. And you'd recognize this right here as being the acceleration in the x direction. So one thing I'd like to point out is that at the end of the day, and I'm going to leave this as dv dt because we're going to integrate this to allow us to find explicit relationships for velocity and also for position. But when you take and you solve this for this, knowing the fact that you have 2 v's here and you have 1 v, so you're going to lose one of those. You get a minus b times l squared over mr times v. So here our acceleration is a function of velocity, and not only that, it's as you can see, we have this minus sign right here that denotes the fact at the end of the day that this is going to be a decaying type behavior. So if you look at what we're being asked here, we're being asked to find how far the ride goes and how long it's going to take for it to do this. So we want to know how far it goes before its final velocity reaches 1/2 of its initial. And we also want to find out how long. So the first step to doing that is to finding velocity as a function of time. So we can start to put together some equations of motion here. We have one for acceleration. This would be the equation for acceleration as a function of velocity. Now, we want to find one for velocity and then one for position. So what I'm going to do is to sort of cross multiply. I'm going to put the v over here and the t over here. And so dv over v is going to equal to minus bl squared over m times r times et. Now, so I'm going to use a little bit of prior knowledge here. When I integrate the left-hand side, you're going to get a natural log. And ultimately, we're going to be taking and raising e to the power of both sides to get the velocity by itself. So on the right-hand side, this is eventually going to be an exponential. It's going to be a decaying exponential because you have this minus sign sitting there. And this conventionally is called a folding time. This is actually 1 over the folding time because we typically write the right-hand side of this as minus dt over tau, and tau is analogous to the RC time constant. So here, tau is going to equal to mr divided by b times l squared. Okay, so I'm going to make this substitution here just to keep track of it and to simplify things and put it in a format that's a little bit more regular. And now we're going to integrate both sides. We're going to go from our initial velocity to whatever our final velocity is going to be. Dv over v on the left-hand side. On the right-hand side, minus 1 over tau, those are constants. And our watch starts at 0 and ends at time t in the future, dt. So the left-hand side, like I said, is pretty easy. This is going to be the natural log of v, evaluated from our initial velocity to our final. On the right-hand side, when you do this, you get minus t over tau. So, if you expand this out and you use logarithmic math, that's the same thing as the natural log of v over v naught on the left-hand side. On the right-hand side, it's minus t over tau. And then, like I said, what we're going to do is we're going to raise e to the power of both sides. And so when you do that, on the left-hand side, you get v over v naught because the e and the natural log cancel each other out. On the right-hand side, you have e to the minus t over tau. And finally, my velocity as a function of time is going to be v naught e to the minus t over tau. Okay, so here's one of our equations of motion right here. Whoops, a little bit too far. So the next thing I'm going to do is to take and integrate this to find my last equation of motion, which would give me my position. So now we know position, velocity, and acceleration, as a function of things. So let's not forget our velocity here, which is in the x direction, is just dx dt. On the right-hand side, we have v naught e to the minus t over tau. And all I'm going to do is to move dt over here to the right-hand side. Dx is equal to v naught e to the minus t over tau dt. And now you just integrate both sides. We'll go from an initial position to our final position. And here we're going from our initial time 0 to our final time t. Now, this is a simple substitution. If I'll let u be minus t over tau, du would be minus dt over tau, meaning that the substitution that I'm looking for is that dt is going to equal to minus tau du. Okay. So, here, on the left-hand side, when I evaluate that integral, I get x minus x naught. So that's my displacement. On the right-hand side, when I take and I plug in what the equivalence for dt would be into this, excuse me, what that does is to put a minus tau v naught out in front. And what's integrable here, and now I'm integrating e to the u du, from 0. Now, when I take and I plug in 0 into t, my bottom limit's still 0. When I plug in t into t up here, my upper limit is going to be minus t over tau. And this is just e to the u. So you go ahead and plug in your limits here. Minus t v naught times e to the minus t over tau minus 1. So now we have an equation for our velocity as a function of time, and we also have our displacement, delta x, as a function of time as well. Right there. Okay. So now we're set. Now we can find things. And in fact, what I'm going to do is let me clear my work area here just a little bit, just so I can make some space under this, since I've done all the calculus here. Let me grab this. I'm going to move over here because we're going to be working with that. And so let's address part B first, because I think what we need to do here is we need to find how long, and then we can plug that in here to find how far it went in that amount of time. So how long is going to come from this? Because what we're trying to find is how long and how far it goes when our final velocity is equal to half of our initial velocity. So if I were to take this right here and plug in my final velocity is 1/2 v naught. And on the right hand side I have v naught e to the minus t over tau, and just cancel things out like that. Ultimately, when I take the natural log of both sides and I disentangle a lot of this, I have t is equal to minus tau times the natural log of 1/2. Okay, so tau, which I guess I must have gotten rid of, but that's okay. We can reconstruct it pretty easily. It was mr over bl squared. Right there. Let me double check that, because it was off the top of my head, but it still should be correct. Oh, here we go. I'll put it on the bottom. Yep, that's it. Okay. So, excuse me. So tau here, let's go ahead and find tau. So tau here is going to be m which is 0.03 kilograms, times R, which is 0.5 ohms, divided by B times L squared. B is a quarter of a Tesla. L is 0.10 or 0.1 meters. And we need to square this right here. So our folding time here is going to be 0.03 times 0.5 divided by 0.25 times 0.1 squared, which is 24. So now what that means is that we can very easily find how long it takes for this thing to go that far. Times the natural log of 0.5. So I get 16.6 seconds approximately. So here's the amount of time right there. Well, knowing that, now we can solve for how far, because we have this equation right here. So delta x, which is how far, is minus tau, which is 24 seconds, times v naught. V naught is 0.25 meters per second. And then we have e to the minus t. T was 16.6 seconds divided by tau, which is 24 seconds, minus 1. So let's see here. 24 times 0.25 times e raised to the power of minus 16.6 divided by 24, then minus 1. So I get right at 3.0 meters. Okay, so how far does the rod go before it reaches half of its initial velocity? About 3 meters. How long does it take for it to do it? About 16.6 seconds. And that's because this rod's velocity is slowly decaying exponentially. All right. Now let's talk about what the current is going to look like. I know the problem itself doesn't specifically ask about that, but remember, we're also trying to get a feel for Lenz's law. And understanding Lenz's law when you have a changing magnetic field is relatively easy, because really all you do is ask about what the direction of the change is. And knowing the direction of the change, you know the direction of the current flow needs to oppose that with respect to its changing magnetic field. So what that does is to help pick UI. But in this particular case, we do not have a changing magnetic field. We have a changing area. Okay? So there are two ways that you could look at this. If you think of the surface normal not as being a unit vector, but looking more like a vector that also is composed of the actual area of this thing, then as this slides to the right, what that means is that my surface normal is changing like that as well. It's getting bigger. Okay? So what that means is that if you chose the direction of your current, it would need to oppose the direction of your changing normal vector, or your changing surface vector. Now there's also another way that you can view this. You could say, okay, if I held the area of this thing fixed, let's just pretend that that's what's fixed. Well, you know, as this thing slides to the right, what it's going to do is to increase the amount of flux, increase the amount of magnetic field that's passing through this thing. So that's analogous to us increasing the magnetic field itself, which means that the increase, the change in magnetic field we would see would be in the z direction, coming straight out at us. That would be the direction of delta B, which incidentally is also the same as the direction of delta S. So what you do is you pick the direction of your current flow that is in the opposite of that direction. Okay? So here, if you were to, say, pretend the current flowed this way, and put your thumb through and then curl your fingers around I, what you would see is that that would be in the same direction as delta B, so it would be a poor choice. But if you chose your current instead flowing this way, now when you take and you put your thumbs in that direction and you curl it around, it opposes what delta B would be. It opposes what delta S would be. So the direction of our eye would be this way around the circuit, because that's the only way that preserves conservation of energy. Okay, so that's it for this video. In the next video, what we're going to do is we're going to continue looking at Faraday's law, except I want to take and apply Stokes' theorem to it. And I also want to look at a specific case, something that we're all intimately familiar with, and that's what about the situation where you're generating electricity? How does that work? And we'll talk about in the next video, and I'll see you then.